Okay, yeah, we have covered the first two chapters on logics and proofs. In chapter 3, we're going to deal with functions and sequences and relations. Okay, and yeah, as you have learned from your middle school years, the functions is defined as this. Let A and B are non-empty sets, and F send an element object in A to an object in B. Then we call this A is the domain, and this B is a codomain, and F is an assignment of exactly one element of B to each element of A, which can be written as F of A is equal to B. Then we call this F is a function on A. And the B is called B is the unique element of B assigned by the function F to the element A of capital A. Then we call B is the image of A, and A is the pre-image of B. So B is the image of A, and A is a pre-image of B. And the set of all images of elements of A is called the range of A, or image of F, the range of F. So F, the functions are sometimes can be mappings or transformations. Okay, send one object in the domain to one object in the codomain. Okay, and the range of S by F of S can be written as this. F of S is a set of T such that there exists a pre-image in S such that T is equal to F of S. So we just write it as a set of F of S where S is in S. So this is the range. Okay, and this D is equal to 60 times T is an example of function when D is a distance, and this number means the velocity and T means time. Then we can think of the traveled miles after certain time T. Okay. Here, in this case, if the domain is a set of all non-negative real numbers, then codomain is also the set of all non-negative real numbers. And in this case, the function is a straight line. So with all the domains, it covers all the real positive non-negative reals. So the range is the set of all non-negative real numbers. Next, the set. This is an errata A. If the set 1 goes to A, and the 2 goes to B, and 3 goes to A like this. 3 goes to A. Yeah, your lecture note has the right one. So you shouldn't have any confusion. The reason that I left some errata, couple of them, is urge you to read critically. Yeah. And so compare to the textbook to fully understand the meanings. Anyway, this is an example of a function, because every element in the domain has the image in codomain. And each element goes to exactly one element in the codomain. So it satisfies the definition of function. So this is an example of a function. In this case, the domain is 1, 2, 3, and the codomain is ABC, and range of F is only this, the set of images A and B's. Okay. And so domain and range are defined in this way. And the important thing is a function F assigns to each X in the domain a unique element Y in the range. This is a very important concept. This is an example which is not a function. Here in this case, 1 goes to A, and 2 goes to A, and 3 goes to B. This looks okay, but this 4 has no image. So there's no image of element 4 in the domain, so it does not satisfy the function, because the element 4 is not assigned to an element in Y, so this is not a function. And also, this is not a function. 1 goes to A, and 2 goes to B, 3 goes to C, and 1 goes to B. In this case, this one element in the domain goes to 2 objects in the codomain, which violates the definition of the function. Okay? So this is not an example of the function. Okay? The function, 1 goes to A, 2 goes to B, 3 goes to C, 1 goes to B, like this. Okay, anyway, this is not it's not a function. Next, f of x is equal to x squared, where the domain of f is a whole real number. Then this is a function, and the codomain is a set of all non-positive, non-negative codomain is all non-negative real numbers, because every real number, the square, is going to be a positive, non-negative numbers. So this is the set of all non-negative real numbers. And ordered pair notations, f is a set of x and x squared, the element in the domain and the image, set of all this, where x is a real numbers. And range of f is all non-negative, non-negative real numbers. Yeah. X squared is positive, not negative. It should be fixed. And you should make a note on these kind of things, so to make sure you understand the whole concept properly. Next, graph of functions. In here, graph of function. You have learned how to draw the graph for quadratic functions. And you know this is a function of one of the examples for the functions. The cubic functions can be drawn. The 5x cubed plus 3x squared minus 4x minus 1 can be written in this way. If you change it as like minus 7 and 7 or 6 or 2, something like that, then you will have, if you copy, and then if you want to draw the graph of it, then you will have this function in here, like this, isn't it? And you can draw any graphs in this. And you can choose any of the language that you want to use. And power function and trigonometric functions, and you can draw the graph of it. You can draw the secant function from minus 2 pi to 2 pi. If you change it to sine or cosine, then you can draw the graph of it without any difficulties. If you can find the large spaces, 8, then you will have the secant. You can draw easily the functions on the web with your smartphone. You can draw the logarithmic functions or exponential when n is from the 1, 2, 3, 4, 5 of the ln of a, and transcendental functions even. So the graph, actually this is the graph of a function, isn't it? Yeah, graph. You can draw all the graphs. Here, you can draw. Let f your function from the set A to the set B. The graph of a function is the set of ordered pairs like this, like you see. Okay, when x was A and f of A is here, B, f of B is there. Collection of all those. Okay, we can think about the function like this. As x is an integer and y is a positive integer, then we define x mod y to be the remainder when x is divided by y. Remainder. This can be a function. Like 6 mod 2, remainder is 0. 5 mod 1, 5 divided by 1, the remainder is 0. And 8 mod 12 is 8. 8 divided by 12 is just, remainder is f. 199,673 is an odd number. So if you divide by 2, then it's odd number. It's going to be 1. This is an example of another function. Okay, this is function, modular function. What what day of week will be 365 days from Wednesday? What day? From today, Wednesday. 365 days. What? How many? Okay. We wanna how many? 300. We want 365 days divided by 7. Yeah. What's the remainder? Remainder is 1. Okay. So which means today is Wednesday. So one more modular is going to be Thursday. So if you 365 mod 7, the remainder is 1. So 365 days from Wednesday, it will be 1 day later, which is a Thursday. Okay. Mm-hmm. If it's about this many days after, then what will be the answer? No, not same. So it's going to be a Monday. Okay, next, ISBN number. Yeah, this you must have seen the ISBN number from your textbook. So this the thing is this number, each of those numbers, those numbers has the meanings. The first part, this is a kind of prefix. Next, the 1 means United States. 89 means Korea. Okay, and then next, this number 59548, that means publishers in United States. 45460 is one publisher in Korea from 89. And then this next 950 is the book number. And the interest, then what is going to be the very last one? This one. How this one? What this one means? Who knows it? Who can explain what that one means? How does it? Error detection number. So here is the explanation of those. When this is on the barcode, and this is when you have this is the algorithms, and this is a barcode. When you scan it, and those numbers, okay, this barcode means these numbers. Okay, the very last digit means this very last digit means error detecting number. So if something's wrong, then we should know. So we do it over and again until we have a right one. So how do we give that number? So suppose we have a 13-digit ISBN number. Let's say it's A, B, C, D, J, K, L, M. Okay, it's a 13-digit number. Then all we have to do is to the computation. 8, the first one, plus 3 times second one, plus third one, plus fourth one times 3, plus fifth one, and 3 times sixth one, and so on. Okay? Then you have some number. And add some number, which makes 0 with mode 10 computation. Okay, so after you do to find a number, then you add a certain number to make it 0 in mode 10. Then every time we need some number to be defined. If you give that number and to make a barcode like that, then when you do scan, if something wrong, at least we can reduce the chance of error by 1/10. Okay. If you do scan 5, 6 times, then it will give you the right numbers. So you don't have to overcharge it. So so this kind of the example is the modular functions are used. Okay, next, the floor function. Yeah, in the exercise problem, you have seen these floor functions. The greatest integer less than or equal to x. If x is in between n and n plus 1, then the least greatest integer less than or equal to this one, so equal to n. This is a floor function. What about the ceiling function? The least integer greater than or equal to. So if x is in between here, then next integer like this. So it's going to be n. Okay, so the floor function of 8.3 is going to be 8. And then floor of ceiling function of minus 11.3 is 11. Okay, floor function of 6 is 6 itself. Okay, so if you do the graph, this is graph of a floor function, and this is a graph of a ceiling function. Okay. Okay. Yeah, you can mark this as what? As empty, or you can use this parenthesis. Okay. Here, if I draw the floor function and ceiling function and print, yeah, the floor function of 8.3 is 8, and ceiling function of 3.5 is 4. Okay. If you draw the floor function here, floor function of from minus 5 to 5. This is the floor function, like what you see. And this is ceiling function from minus 5 to 5. Okay, it's above and it's a bottom. Okay, so between here and here, 1 to 0 is going to be 0, but on the ceiling function from 0 to 1 is 1. Okay, okay, if you draw those together, then you will see this ceiling function and floor functions at once. Okay, you can draw. Yeah, this is one way of using it. This is a Python-based graph. And Sage next. With those notation in 2007, U.S. first-class postage rate for retail mail up to 13 ounces was 80 cents for the first ounce or fraction thereof, and 17 cents for each additional ounce or fractional postage, P of W as a function of weight W, which can be defined in this way. For the postage, price of postage based on weight, we are using these floor functions. Okay, these ceiling functions like this. If the weight is this much, then the price is fixed here until that weight. If above that, then price go up. Like this. So, and the quotient and remainder theorem is also we have learned this. If the integer is like this, then divide by d, you obtain this. And here, on this we do, if we do the floor functions, then this we can compute q as the floor function of n over d. Then having computed the quotient, we compute the remainder like this. Okay. In this case, the remainder r can be considered as n mod d, because this is a remainder when n is divided by d, the remainder. So n mod d is going to be the remainder. The remainder can be defined in that way, like what we did on the calendars. The concept here, one-to-one functions, which is called the injective function. One-to-one function is a function from x to y. If for each y in y, there is at most one x in x with f of x is y, then this function is called injective. And this is a one-to-one function, and it is also called as an injective function. So for example, if function a from a to b is 1 to 1, then for all a and for all b, f of a equal f of v implies a is equal to b. If f of v and f of a are same, then a and b should be same. That's the concept of one-to-one function. So if equivalently, if for all for a, if a is not equal to v implies f of a is not equal to f of v, the same thing. So this is a one-to-one functions. Those can be written as this. So f of one-to-one, if and only if this satisfies or this satisfies. Okay. So for example, this function is one-to-one. Here, 1 goes to S, B goes to U, C goes to R, D goes to A. So, if f of a, if f of this is not. If f of a is equal to f of v, then f of a is equal to. In this case, f of a is equal to S, f of d is equal to S. So this is not an example of one-to-one. But this is one-to-one. Yeah. 1 goes to B, 3 goes to A, 2 goes to C. Ah, I see. But here, why? Here, this is one-to-one. Yeah, this is one-to-one. But this is not one-to-one. Okay. The function, this is not one-to-one. 1 goes to A, 2 goes to B, and 3 goes to A, like this. This is an example of this. Here, f of 1 and f of 3 are same, but 1 is not same as 3. So it violates the condition of one-to-one. So this is example of one-to-one and not one-to-one. Here, if like this, if we have 3 and 3's like this, then it is one-to-one. But if you have one common one like this, then this is not one-to-one. So the one-to-one and not one-to-one. Prove that a function f of n is equal to n plus 1 is one-to-one. How do you show? For arbitrary n1 and n2, let f of n1 and n2 f equal to f of n2. Show n1 is equal to n2. Then it's done. So we write down f of n1, which is 2n1 plus 1, is equal to 2n2 plus 1. And so I subtract minus 1 on both sides and divide by 2, then we have n1 equal to n2. So this implies that, so it is one-to-one. Done. In other words, a function is not one-to-one if there exists x1 and x2 such that f of x1 is equal to f of x2 and x1 is not equal to x2. If we have this, if there exists x1 and x2 that satisfies this, then clearly it's not one-to-one. So this is the way to showing a given function is not one-to-one. Like this. F of n is equal to 4 to the n minus n to the 4. Then if we choose n1 and n2 as 2 and 4, then f of 2 and f of 4 are same, but 2 is not same as 4. So there exists this x1 and x2, 2 and 4 satisfies this. So it is not one-to-one. Next, onto. Surjective function. If function f from x to y, the range of f is y, then f is said to be onto y. We call it onto function, or surjective function. This onto means for every element in B in capital B, there exists an element A in capital A with f of a is equal to b. Then we call this function is surjective or onto. Which means if it has a preimage, every element in the codomain has a preimage in the domain, then we call it is onto function. Like this. This 1 goes to A, 2 goes to C, 3 goes to B. Then this is, if x and y are these three elements, then that's a one-to-one. And also, everyone has a preimage, so it's onto. So one-to-one and onto. But this function is not onto because here D in the codomain does not have a preimage, so it is not onto. It's one-to-one but onto, but not onto. Bijection. If a function is both one-to-one and onto, then we call it is a bijection, like this. From 1 to 3 to A, B, C, 1 goes to A, 2 goes to C, 3 goes to B. Clearly, 3 goes to 3, all different. 1 to 1 and 1 to, so it's bijections. Okay? If two sets are cardinal, the set of two, cardinality of two sets are same, there always exists a one-to-one function and bijective function. Inverse function, you must have learned it. If function is one-to-one and one-to from A to B, then there exists one-to-one and one-to function from B to A, which is called F inverse. This is an inverse function. Inverse function can be defined in this way: BA, where F of AB is in F, and B set of BAs is called F inverse. Like F goes here and F inverse, and this element to the back. An inverse function, and this the inverse function of this is 2 goes to A, 3 goes to B, 1 goes to C. That's the inverse function. Can be written in this coordinate notations. An inverse function allow function if F allow arrow diagram for simply reversing the direction. F goes here and F inverse go the other directions. Next, composition, 합성함수, composition. If we have two functions f and g from x to y and y to g, then composite function from f circle g is a function that sends x to the g of x, then f of g of x, like this. So this composite function is a function from x to g. This composite function. So this is an example of composite functions. If g is this and f is this, then f circle g is send 1 to y, 2 to y, 3 to g, like this. Okay. Okay. Binary operators. And a function x cross x, Cartesian product 2x is a binary operator. Choose two elements from x and cross product sent to an element in x. We call it a binary operator. For example, x is natural numbers, the set of natural numbers, and f of x, y is equal to x plus y. If you choose two natural numbers, the addition is another natural numbers. This is an example of binary operators. And the conjunction and disjunctions and implies and if and only are all binary operators. Unary operator on the set x associated with each element of in x or one element in x, unary. From a function from x to x. Send an element in x to an element in the same set. And you call it an unary operator. These are all the examples of functions. Okay? And for the universal set, the complement is also an example of unary operator. In a set, you choose a subset there. And function send from here to the complement of that set that is in X. So that's another example of operator. So you are learning the new functions that you have used. So we can use all those knowledges from chapter 1 and 2 on chapter 3 on functions with this. If X is a set of proposition, then negation is also a unary operator. Negation. Statement and the negation of it. Okay, I think that's the end of section 3.1. And there are examples like this that has been solved. You can see those in where you can see the examples here and the solutions. You can see the solutions. These solutions of chapter 3 here, and go through it and try to solve the new problems. Change the problems. You have a solutions here. So you try to understand the solutions and make a changes on the problem and discuss. And also if you do not understand the solutions and problems on this website that I made last semester to help you to understand, then ask questions. Okay, that's the end of today's class. Any questions?